In this video, we consider the frequency response of discrete time systems represented by linear difference equations. The transfer function, or system function h of z, of a discrete time system described by a linear difference equation with constant coefficients is given by the following expression. H of z is equal to p of z over q of z. P is a polynomial representing the time delay or time advance operators acting on our input signal. Q is a polynomial representing the time delay or time advance operators acting on the output signal. We can also think of h of z as being the z transform of the impulse response h of n of the system. Note that here we've assumed that the impulse response is going to be causal, so the sum only starts from 0 to infinity. The impulse response of a discrete time system represented by a linear difference equation can be given by the following form. It may include an impulse function, and it will include a linear combination of the characteristic modes of the system. If the system is causal and stable, then all of the characteristic roots are going to lie inside the unit circle. That means that the region of convergence of h of z, or the region of convergence for the z transform of h of n, will contain the unit circle. And so we can evaluate h of z for any value of z equal to e to the j omega on the unit circle. So h of z equal to e to the j omega, or h of e to the j omega, is known as the frequency response of the system. Let's consider the response of the system to the everlasting exponential input signal x of n is equal to e to the j omega n. The output response of the system y of n is given by a convolution between the impulse response as well as the input signal, and that's shown by the convolution sum over here. We can replace x with e to the j omega n, and this will give the following in the convolution sum. We can pull out the term e to the j omega n because this does not depend on the summation variable k. So that leaves us with the following expression, and we could identify this term over here as the discrete time Fourier transform of h of n. So this is effectively h of omega, or h of e to the j omega. That means that the output signal y of n is going to be e to the j omega n, so it's the same everlasting complex exponential signal at the input, but it's going to be scaled by the frequency response of the system. And the frequency response is going to be evaluated at the frequency of the input complex exponential signal. We now consider the response of the system to an everlasting sinusoidal signal. If the system is stable and it has a real impulse response, in other words, h complex conjugate of n is the same as h of n, then we can show that the frequency response will obey the following. H complex conjugate of omega is going to be h of minus omega. So if we put the everlasting sinusoidal signal x of n is equal to cosine omega n as the input to the system, then the output response y of n is going to be the same cosinusoidal signal, so we'll have cosine omega n, but the amplitude is going to be scaled by the magnitude of the frequency response evaluated at the same frequency of the sinusoidal input signal, and the phase of the sinusoid is going to be shifted by the angle of the frequency response h evaluated at the frequency of the sinusoidal signal. Let's consider an example. We want to obtain the response of the LTI system described by this difference equation subject to the input signal x of n is equal to cosine pi over 6n minus 0.2. If we take z transforms of the equation, then we'll have the following. Y of z times 1 minus 0.8 z to the minus 1 should be equal to x of z. H of z is going to be given by y of z over x of z, and so in this case this is going to be 1 over 1 minus 0.8 z to the minus 1. If I want to obtain the frequency response, I evaluate h of z for z is equal to e to the j omega. In this case I have z to the minus 1, so instead of e to the j omega I could replace this with e to the minus j omega. So h of e to the j omega is going to be 1 over 1 minus 0.8 e to the minus j omega, which I can also write as 1 minus 0.8 cosine of omega plus j 0.8 sine of omega. So the frequency response of the system is given by the following expression, and I could obtain the magnitude, which is shown here, as well as the phase, which is shown over here. The plots show the magnitude response as well as the phase response. Note, of course, that because this is a discrete time Fourier transform, the magnitude and or the phase response are going to be periodic with period 2 pi. The amplitude and the phase of the frequency response of the system is shown over here. Our input signal is x of n is equal to cosine pi over 6n minus 0.2. So the output of the system is simply going to be given by cosine pi over 6n minus 0.2, and I have to scale the amplitude of the cosine by the magnitude of the frequency response at the frequency of the cosine signal. So for here, I would put omega is equal to pi over 6. I also have to shift the phase of the sinusoidal signal by the angle of the frequency response of the system. So that's angle of h, and I'm going to evaluate the above expression for omega is equal to pi over 6. So if we do a plot, x of n, which is our sinusoidal signal cosine pi over 6n minus 0.2, is shown over here. The output signal is going to be shown over here. So it's going to be changed in amplitude by the amount here, and it's going to be shifted in phase by the angle amount shown over here. We now consider the response of the system to a causal exponential signal. So we have a stable LTI system described by a linear difference equation, and the input signal is a causal exponential signal of the form x of n is equal to e to the j omega n times u of n. The output response of a system can also be broken down into a sum of the steady state and the transient components. The transient component is the part of the output that's going to die to zero as n goes to infinity, whereas the steady state is the part of the output that's going to persist for all of time. So, the only way we can have a steady state output is if the input signal will also persist for all of time. So that's shown over here, e to the j omega n times u of n. So the steady state output is going to be given by e to the j omega n times u of n. That's the same as the input signal, but that's going to be modified by the frequency response of the system evaluated at the frequency of the input exponential signal. The transient solution is going to be given by a linear combination of the characteristic modes of the system. Since the system is stable, all the characteristic roots are going to lie within the unit circle. So clearly this transient response is going to die to zero as n goes to infinity, and we'll be left with simply this part, which is going to persist for all of time. We now consider the response to a causal sinusoidal signal. So x of n is cosine omega n times u of n. If the linear difference equation has real coefficients, then we can show that the steady state and the transient solutions are going to be given by the following expressions. The transient solution is still going to contain a linear combination of the characteristic modes, and these will die down to zero as n goes to infinity, because if the system is stable, all the characteristic roots lie within the unit circle. The steady state solution is going to involve the same causal sinusoidal signal, so cosine omega n times u of n, but the amplitude is going to be modified by the magnitude of the frequency response evaluated at the frequency of the sinusoid, and the angle of the sinusoid is going to be shifted by the angle of the frequency response, or the phase of the frequency response evaluated at the frequency of the sinusoid. And a similar result will hold if we use as our input signal x of n is equal to sine omega n times u of n. If you have any questions, please send me an email.